Good day, everyone, and welcome to our webinar titled Assessing Steel Pipeline and Weld Susceptibility to Hydrogen Embrittlement. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our website in about 10 days. We will send out an email to attendees once those are posted to the site. All attendees will be on mute throughout the webinar, so please submit your questions via the questions box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. With that, I would like to introduce our DOE host, Neha Rustagi, joining us from the Department of Energy headquarters in Washington, D.C. Neha has been a technology manager within the Hydrogen Production and Delivery Program at the Fuel Cell Technologies Office since November. Prior to her current role, she supported FCTO as a fellow since 2014. She obtained a master's in mechanical engineering from the University of Colorado Boulder in 2012 and conducted her thesis research on the modeling of hydrogen-assisted fatigue crack growth. It's a pleasure to have you, Neha. Good afternoon.
Thank you, Chris. Our presenter today is Dr. Joe Ranovich from Sandia National Laboratory. Joe has been with Sandia's Hydrogen Effects on Materials Laboratory since 2012 and focuses on hydrogen embrittlement of structural materials with a particular emphasis on welds and pipeline carbon steels and stainless steels. In addition to funding from the Fuel Cell Technologies Office, he received an Early Career Laboratory-Directed Research and Development Award in 2015 to support his research on measuring hydrogen concentrations ahead of crack tips. Prior to Sandia, Joe received his PhD from the Colorado School of Mines in Metallurgical and Materials Engineering. During his time at Sandia, Joe has been working closely with Dr. Brian Summerday, who many of you probably know. Brian was originally going to join us on this webinar, but got called into jury duty, so Joe will be presenting for both of them. Brian has been at Sandia for 18 years, leading Effects on Materials Laboratory and serving as a PI on numerous R&D projects related to embrittlement of structural materials in hydrogen gas environments, including projects that supported the Fuel Cell Technology Office's mission. He will be transitioning from Sandia to Southwest Research Institute in San Antonio, Texas this spring. At SWRI, he will apply his expertise in hydrogen embrittlement to applied R&D projects focused on structural metals in wet H2S. Since Brian expects to remain active in the hydrogen embrittlement community, he expects to continue crossing paths with many of you. And with that, I'm going to turn it over to Joe.
Thank you, Neha. So the title of my talk today is Assessing Steel Pipeline and Weld Susceptibility to Hydrogen Embrittlement. And really, this work has come about because it was kind of noticed that in the literature, there really wasn't a lot of research performed specifically on welds in a hydrogen environment. So with that, I'd like to first acknowledge my colleague, Brian Summerday, for his help with a lot of the research that we've done, as well as putting together these slides today, as well as the funding we've received from the Fuel Cell Technology Office. Now, I put the acknowledgements up front because oftentimes they get pushed towards the back, and I feel like it really is necessary to acknowledge the people and collaborators we've worked on because this work really wouldn't be possible without their presence and their help. So first is our Hydrogen Effects on Materials Laboratory, which is located here at Sandia National Lab. And this houses our core capability of testing these pipeline steels in high hydrogen pressures in a dynamic system. And along with the core capability of the infrastructure, there's also the core capability of the people. And I think that makes a huge difference. The other feature, the other collaborations we have is with several different national laboratories, Oak Ridge National Lab, as well as NIST in Boulder. We also have some relationships with the academic world, in particular the International Institute for Carbon Neutral Energy Research, which is located in Japan. We have some industry partners, particularly ExxonMobil, who supplied us with one of our pipes that we examined. And then finally ASME, who is developing the codes for a hydrogen pipeline, because ultimately when a pipeline engineer wants to design a hydrogen pipe, they are going to be using the codes that are developed by ASME. So we work very closely with them to ensure that the testing we're doing is relevant and on industrially relevant materials. So just a brief agenda. First, I'll just kind of discuss why do we want to look at steel hydrogen pipelines. Why is that our focus? The different objectives that we are looking into in terms of the research we're doing and why we're performing it. We're looking at several different variables and how those affect hydrogen embrittlement of steels. So I'll go through the approach and then just a brief summary of our results and our conclusion, and kind of a look forward as to what our future research will be. So in a hydrogen economy, really the infrastructure necessary to transport hydrogen from a centralized gas production facility ultimately to the final stage, which is the fueling station, requires many different components to be exposed to hydrogen gas. So hydrogen must be, in the gaseous form, must be compressed, and then finally transmitted over many miles of pipe. There's various storage facilities along the way and distribution pipes. And so where our group at Sandia really fits in particular to this presentation, is really with the transmission pipeline. That's the area where we're focused on. And so it was acknowledged that the structural materials are really central to driving the cost and the reliability of the hydrogen infrastructure. So in terms of what a hydrogen pipeline will look like, or what the process of assembly and installation will look like, there's a couple of nice view graphs here, or images in these view graphs, where the pipeline will really consist of mild to moderate strength pipeline microstructures, such as X52 or X65 line pipe. And these segments will be laid out and essentially butted together and girth welded. So welding is one aspect that we need to basically ensure we don't overlook, because oftentimes welding can introduce other potential defects into the microstructure that we want to make sure we're looking at. So I've highlighted two different welding processes. Gas metal arc welding, which is kind of what captured in this image, where you see this is the more traditional type welding, where it's a consumable weld. It requires consumable filler metal as well as shielding gas. And this is what you typically think of when you think of a weld, where the metal is melted and then it forms a joint between two butted up pieces of metal. Now the friction stir welding is another welding technique that is a little bit more modern and is a solid state weld. It requires no consumables. Essentially the weld pieces are placed together. A tool is then inserted and then rotated at a high RPM that allows softening of the material and stirring of the material. And so these are just two different welds that we'll take a little bit closer look at during this presentation. And then finally, in the bottom right is the final product. So we have a pipeline that will be welded together via different methods, either gas metal arc welding or friction stir welding, and then inserted into the ground. And in a mature hydrogen economy, or a mature hydrogen pipe will experience different demands on the pressures in order to supply and meet those demands. So the daily pressure fluctuations we will anticipate may occur several times a day. And what happens as the pressure begins to fluctuate, as we see fatigue loading incurred on the pipe. And this can affect the embrittlement mechanism. So the three areas, or three variables that I'm kind of focused on in this talk are: how does the microstructure respond? How does that play a role in the fatigue crack growth rates in these pipes? As I mentioned, welds are always really the lack of literature out there on welding until recently really made us become aware that we need to perform more testing and ensure the reliability of the welds. And then finally, with respect to the embrittlement, I'll talk at the very end just about the potential benefits we can have of having gas impurities in the stream itself and how they can mitigate the embrittlement effect. So just a little background on hydrogen embrittlement, just in the physics of it. If you'll imagine now we have this gray region here, which we can call our steel pipe. And we have some critical flaw, or we have some flaw on the right side here that is representative of some defect. Now in the presence of a stress, we can use fracture mechanics to understand what the K is, or the stress intensity factor. That is due to some remote stress that's applied on the pipe. But what's really important is the local stresses and strains at the crack tip. So really what's going on that's helping to drive the hydrogen to a specific site, and what's happening in the local region is where we truly want to understand what's going on. So if hydrogen is present, that doesn't necessarily indicate that we will have hydrogen embrittlement. There are many steps that actually need to occur in order for hydrogen to get to the site where it can cause embrittlement, and those are often overlooked, and we just assume if there's hydrogen, then there's hydrogen embrittlement. But really what has to happen is multiple steps. So first, the hydrogen has to be able to transport down the crack tunnel, essentially reaching the crack tip in order for, so basically it becomes a supply issue. Can that hydrogen get to the site where it needs to, or where it may cause embrittlement? The second step is that the hydrogen is in diatomic form. It needs to dissociate and chemisorb on the surface. This is just one of the possible limiting effects, but hydrogen does need to dissociate onto the surface. And then it can finally absorb into the material and move to these regions of higher stress and take part in this embrittlement effect. So the three variables that we're going to look at first is related to, once there's hydrogen in the material, how does it interact with the microstructure? In particular, we're going to look at some welds and really the role that residual stress can have. Because anytime you're talking about welds, what you're really introducing are potential changes in residual stress. The other area that we're going to look at is the effect that microstructural banding can have on hydrogen embrittlement. And banding is not necessarily desirable. It definitely is not a desirable microstructure, but it does give us the opportunity to examine how different orientations behave if we propagated the cracks in different orientations. And then finally, we're going to look at how does gas impurities, in particular oxygen, play a role in hydrogen uptake. So the three different regions we're going to look at and how they influence hydrogen-assisted cracking are the microstructure, stress, and then finally hydrogen uptake. So the question of why should we use steel hydrogen pipeline? I just identified steel has susceptibility to hydrogen. But the reality is we have a lot of confidence in steel. We've been operating pipelines for many years, especially the oil and gas industry, and they're quite robust. They're quite resistant to third-party damage during installation, backhoe, whatever it may be. They're quite robust material. The reality is the idea of a hydrogen pipeline made out of steel is not unique. In fact, there are over 1,500 miles of steel hydrogen pipelines already in use in the U.S. The difference is that these pipelines have been operated very safely, but they've been operated predominantly under constant pressure conditions. And the reason of that is that the demand has been pretty constant, and therefore you can supply a constant pressure to meet those demands. Now, in a mature hydrogen market, the demands we anticipate will fluctuate throughout the day, throughout the year, throughout the season, and therefore we're going to introduce fluctuations in the loads to our microstructure or to our pipeline, and so we need to be aware of how the base metal and the welds really behave to these fluctuating loads. So along with that, we want to basically perform experiments that are realistic. In other words, that we're testing service conditions that we actually anticipate the pipe to experience, and this will help to optimize our design codes so that we can essentially not over design our pipe so that it's costing us this huge premium. And this will help ensure our reliability of our pipe. And then finally, as we are growing this knowledge in performing these experiments on different microstructures, we're beginning to develop this microstructure understanding on how does the microstructure truly affect the fatigue crack growth rates of steel. And this will help us in future development of novel steels where we can maybe tailor in a specific microstructure that is more resistant to hydrogen. And that would be obviously an added benefit from cost and reliability. So all of these components and objectives that we're working towards are really just to enable a risk-informed design to ultimately lower the cost of pipeline steels. So the approach that we're taking is here at Sandia, we have our core capabilities in our hydrogen effects on materials lab, and we're able to perform these tests in high-pressure hydrogen gas. And so we're choosing industrially relevant pipeline grades, and we're testing them in a service environment that we anticipate these hydrogen pipelines to be exposed to. So the fatigue crack growth data that we generate is the basis for what's going into the ASME B3112 code, which is the code that, as I mentioned earlier, will be used by a pipeline designer to spec out what size thickness and what size diameter, all of these specs that will be necessary if they're wanting to put in a hydrogen pipeline. I have two different welds shown here, and these are the two welds that we're going to be looking at. And so we're going to be looking at differences in microstructure, differences in microstructural banding, and then, as I mentioned before, at the end I'll kind of touch on it briefly about how gas impurities can actually have somewhat of a beneficial effect. So the two pipelines we looked at are X65, which is girth welded, and it was produced during using a gas metal arc weld. Gas metal arc weld is a MIG welding process in which the weld is built up through consumables, and it's a multi-pass weld. You can see that the microstructure of the fusion zone is distinctly different than, let's say, the base metal. And you can actually see kind of this halo region around the weld where you have the heat affected zone. Now, the other pipe we looked at was an X52 pipe, and this was also girth welded, but this was girth welded using friction stir welding. And as I mentioned, the welding process is completely different. There's actually no melted metal. It is actually just friction produced by the stirring process softens the metal and allows it to mix. And so the microstructure, the resultant microstructure is actually quite similar to the base metal. And so we looked at these different microstructures between the base metal and the weld. So first, looking at the X65, we see that if you look at the middle of the screen here at the three different orientations of the pipe, I have called them out as L, C, and R. Because this was supplied to us as a pipe, the L stands for the longitudinal direction, C for circumferential, and R for radial. And you can see this actually was a banded microstructure to begin with. And what I mean by that is if you look in the L and C planes, you see these distinct regions of the darker phase, which is the pearlitic phase, or pearlitic region, and then the lighter phase is the ferrite. And so this is just an artifact of the processing technique. During original solidification, you end up with this banded microstructure. But the microstructure overall for the base metal was a ferrite pearlite microstructure. The weld microstructure itself was distinctly different from a ferrite pearlite. It was various morphologies of ferrite, including grain boundary ferrite, allotriomorphic, and some Binman-Staton ferrite, as well as some dispersed carbides. But it was a refined microstructure as compared to the base metal. And then the heat affected zone microstructure really was appeared to be like an annealed base metal, an annealed ferrite pearlite, which is really what had happened, because as the welding process heats up, that heat is absorbed into the surrounding material, and it affects the microstructure around it. So this was the first set of microstructures we looked at. And I've kind of used this schematic. I'll use it throughout the talk it'll kind of help guide where specimens were extracted with respect to the weld, and it shows the different orientations. So that's what these L, R, and C values mean. So we also looked at a friction stir weld. And so this was a thinner pipe, a thinner walled pipe, I should say. And we extracted specimens out of the center of the fusion zone, as well as an off-center region, and then of the base metal. And these dashed lines in this case represent really the crack plane, and in this case they'd be moving in and out of the screen. So that's really where we situated the specimens so that we'd be testing a more or less uniform microstructure as the crack progressed through the material. So the base metal microstructure consisted of a ferrite pearlite microstructure. The friction stir weld didn't look all that different, although it did have not as much pearlite. It had more dispersed carbides throughout the microstructure. And then the off-center region looked fairly similar to the base metal. But we really wanted to get a good overall characterization of how the different microstructures are going to behave in this friction stir weld. So our testing capabilities here at Sandia in our hydrogen effects on materials lab essentially are centered around this component in the bottom left, which is our custom-built pressure vessel that has been put into a servo-hydraulic load frame, commercially purchased servo-hydraulic load frame. And the way it works is that the top end cap of the pressure vessel is fixed to the crosshead. The bottom actuator, the actuator essentially penetrates through the bottom of the pressure vessel and fixes to our specimen and allows us to apply a dynamic load under high pressure conditions. Now we did use two different specimen geometries, and those were really just to match our material constraints that we had. So we tested compact tension specimens as well as single edge notch tension specimens. So the loading that we really applied on this, as I mentioned, we consulted with the ASME P3112 committee, and it's kind of an optimization of testing frequency and R ratio. And so these tests were performed at an R ratio of 0.5. What that means is this is representing, if we say the maximum pressure of our pressure vessel is 3,000 psi, we're cycling between maximum pressure and half the maximum pressure, so 1,500 up to 3,000. That's what we're really trying to simulate by this. The frequency that we tested at was at 1 hertz, and this became a balance of testing at lower frequencies. We've shown or observed that the effects of hydrogen can be more dramatic or more enhanced, but really it's an optimization because testing at lower frequencies obviously requires a larger amount of time for the test to complete. So that's kind of the parameters that we settled on for the majority of our tests. The supply gas that we tested on or in was 6,9 hydrogen, and then the pressure, as I mentioned, was 21 MPa, or in English units, 3,000 psi hydrogen. And all the tests were performed at room temperature. So in order to really optimize what we're trying to do here, we really want to perform experiments in the condition that is most similar to what the pipeline will experience. So we can do these tests in high purity hydrogen gas. We can develop T-crack growth curves that look just like this. And essentially, from that, we can incorporate them into a fatigue life analysis that's based on fracture mechanics approach. So in other words, if we have a pipe and we know that we want to move a certain volume through it, so that dictates a little bit of the radius. We assume we have an initial flaw, which is identified here as A. We can then use these experimentally measured fatigue crack growth curves and essentially get a fatigue life of the pipe. And so if we have a pipe that we want to say lasts for 50 years, we know what the critical crack depth is. And so if we design with a safety factor in there of 2, so we want to design the pipe so that we get 50 years of life and the crack is still only at half the critical depth, we can do those type of calculations now that we have experimental results from fatigue crack growth relationships. And so that's just really what the ultimate goal of our work is. We're doing a lot of the experimental work, but it's nice to see, and I'll show a calculation towards the end of the discussion that shows how we've incorporated our measurements into these calculations to predict what thickness pipe is required to satisfy this criteria. So the results now of the X65 gas metal arc weld, as I mentioned, these schematics up here really just serve as kind of a legend for the fatigue crack growth curves. So we did test in the fusion zone. They also show what specimen geometry was tested for each condition. So in other words, we performed tests of the fusion zone here in blue, the heat affected zone in red, and then of the base metal in black. And so what we have here are the fatigue crack growth curves. So just backing up slightly, what this curve really represents is on the x-axis we have the delta K applied. And really what that is the stress intensity factor applied, or in other words, the driving force that we're supplying to get something to happen. The y-axis is the crack growth rate. That's really the material response. So we're basically applying a driving force and we're measuring the material response. So as you look at these curves, first of all, of the base metal tested in air, as you see in the black here, this is the typical trend that you see in a more inert or air environment, where you see a very linear trend with increasing delta K applied, you get an increasing crack growth rate, and that linear response is pretty common. The terminology of hydrogen accelerated fatigue crack growth really comes from, if you look at these lower delta K regions, you can see the 3 different microstructural regions we tested were the fusion zone, base metal, and heat affected zone. And you see that the crack growth rates begin to accelerate at these lower delta K regions. And this is where the terminology hydrogen accelerated fatigue crack growth comes from. So in general, all 3 of these showed similar relationships on a very macro scale. In other words, at lower delta Ks, they became somewhat coincident with the data in air. And then you begin to see that they accelerate quite rapidly and then somewhat follow a similar slope as the data in air, albeit they're about an order of magnitude faster crack growth rates than they are in air. Now looking more closer at the details, we did run triplicate tests of each condition. We saw good repeatability among triplicate tests. But specifically looking at the lower delta K region, which is important because the likelihood of us actually running a pipe at these higher delta Ks, more than likely these are going to be at much lower stresses that we're going to be seeing on the pipe. But nonetheless, you see that overall the fusion zone at the lower delta Ks showed a slightly higher crack growth rate than the base metal did, or the heat affected zone. And then at the lower crack growth rate of the heat affected zone, we actually saw a slightly lower crack growth rate in the red here than we did at the base metal black. One thing we did notice is, one, we do know that this pipe does possess residual stress. Now, residual stresses are innate due to the welding process, and actually there was some other research done on this pipe that did show some significant residual stresses. And so what we're really interested in is really understanding what the effects of the microstructure are to the unknown driving force. And really the residual stress helps to, it kind of is masked a little bit in what our driving force is in this case. So we knew we needed to perform a little bit more analysis to kind of tease out what was going on with residual stress and how was that influencing our applied driving force, or the effective driving force, I guess. So we did some further analysis specifically on the heat affected zone. And what we found was when we removed the effects of residual stress, we got a shift in the curves. And I've identified them as the non-corrected version, which was what we saw on the previous slide, and the corrected version that's shown now on the red dash line. And so really what this dAdN delta K curve shows us now is that the once you remove the effects of residual stress and you're using a known driving force, you can actually measure the material response more accurately and more reliably. The reason we're doing this is that a 1-inch thick weld pipe that is welded together is going to have different residual stresses than a 1/4-inch thick weld pipe or a 1/2-inch thick weld pipe. So the fatigue crack growth curves on the previous slide really don't differentiate that. It's just what that exact pipe is. And our ultimate goal is to characterize the intrinsic microstructural response to hydrogen. And we can't do that if we're kind of masked by some residual stress. So this essentially represents a more accurate presentation of what's going on with heat affected zone microstructure as opposed to the base metal. Now we also looked at an X52 friction stir welded pipe, and as I show here in the schematic on the right, we looked at 3 different areas. The base metal, the blue is the center of the fusion zone, or center of the friction stir weld, I should say, and then the off-center region is shown in red. And as I mentioned before, the dashed lines represent the areas where the crack plane would be propagating through. The results of these base metal, first of all, the base metal and air shows very similar trends to what we saw with the X65, a very linear response. And we also see hydrogen accelerated fatigue crack growth in these X52 pipe. The 3 areas, friction stir weld, had a slightly higher crack growth rate than the base metal, which is slightly higher than the off-center region. And once again, we saw very good reproducibility or repeatability among triplicate tests. So what happens when we take all this data of all the welds that we've tested and put them on one? Now, I've only used single curves for these because it got a little messy if we try to plot them all. But what you see here is you have the X65 girth weld, which was a gas metal arc weld, the X52 friction stir weld, and then we also borrowed some data from our friends at NIST, and they'd done some testing on the X52 vintage girth weld, so it was a weld made many years ago. And what you see is the overall trend is that they're behaving quite similar, especially when we compare them to an X52 base metal. And so this is very encouraging because it basically opens the door for other welding techniques such as this friction stir welding, and we see that we're gaining confidence in the reliability of that weld. Now we also took some little bit of liberties in the fact that we had a banded microstructure. So one of the questions that comes up is how does microstructure really impact the fatigue crack growth rate? Does it really have much of an effect, or is it that dramatic, or can we call it all kind of the same material? And so even though this is a ferrite perlite steel, the fact that it is banded gives us the capabilities to, if we test the material in different orientations, in other words, if we propagate the crack through the microstructure, for instance, CL and the LC orientation, these dashed lines represent the crack plane. You can see that they're kind of encountering the same microstructure as they propagate through that cube of microstructure that we see there. They're essentially parallel planes of ferrite and perlite, and so maybe they're going to behave similarly. That's what we would anticipate. The LR orientation, as you can see on the top of the cube, is now propagating through these layers of ferrite and perlite. So in other words, they're alternating layers. So although a banded microstructure is far removed from what we would call a technologically optimal microstructure to look at, we can use the fact that we have this pipe in our hands, or this material in our hands, and do testing, which will allow us to really see what the effects of microstructure are, and really different extremes. So what we found was the data in air, as I said, is consistent between the X65 and the X52 from the previous few slides. But what we see is that the CL orientation and the LC orientation showed a little bit of difference at the lower delta Ks, but really started to converge at the higher delta K region. But the LR orientation was very interesting because it showed lower crack growth rates throughout the entire delta K space, or delta K range that we tested at. And this really highlights that microstructure does seem to have an influence in how these crack growth rates are occurring. And the way we have kind of tried to understand this is there's kind of two parts that really have to happen in order for hydrogen embrittlement to occur in this situation. We need to actually have a sufficient supply of hydrogen, and we need to have a sufficient driving force. So this first box on the left really shows that the hydrogen diffusion in the LR orientation must diffuse through regions of alternating ferrite and pearlite. And the diffusivity in pearlite is lower than in ferrite, so overall the effective diffusivity is going to be reduced if we're trying to move hydrogen in this direction, because this is the way the crack tip would be propagating through, so we need to get the hydrogen ahead of that crack tip. Now contrast that with the CL orientation, in which we have these short circuit pathways for the hydrogen to diffuse through the ferrite, and hydrogen therefore is going to be able to move through there much more quickly, and therefore we won't have a hydrogen supply issue. On the right, we see the presence of cracks propagating through a banded ferrite pearlite microstructure, and in the LR orientation, what we actually observed was crack branching occurring. So as the crack approaches these harder regions of pearlite, it actually branches, and in effect, what that does is it shields the crack tip from seeing the entire driving force, or the whole stress that is applied, and so therefore reducing the driving force. So these two factors basically reduced hydrogen diffusion, which ultimately results in a lower hydrogen supply, or a delayed hydrogen supply, we'll say, and the presence of crack branching shows that the microstructure does have an influence. And so when we compare the results of this banding microstructural study to a whole bunch of pipelines that have now been examined in the literature, essentially between us at Sandia and NIST, what we see is that despite the difference in microstructure, which we'll see between all the different pipeline grades from X52 to X70 to X80, those all tend to fall in this kind of narrow band of fatigue crack growth rates. And really the outlier is this LR orientation. And so this just gives us a little bit more insight that the microstructure really is playing a role. And it's not necessarily related directly to strength, because X80 steel is going to be much stronger than an X52, but really we need to be paying attention to what the microstructure is doing. So now we've measured the fatigue crack growth behavior, and now we can use that to help calculate what a minimum wall thickness may be needed for hydrogen steel pipes. So what we did was we basically said, okay, we want to have a pipe that lasts 50 years, and we would assume that we have 2 cycles a day that's occurring on that pipe. And so we know there's 2 variables that we kind of analyzed. There's many variables that affect this, but the 2 that kind of have one of the most dramatic effects are the pressure ranges that we're actually testing at. So in this case, in bold, we see the 3,000, this would be a pressure pipe cycling between 3,000 psi down to 1,500 psi twice a day for 50 years. The other critical variable is the initial flaw depth. So we assumed that with modern technology, we could probably measure wall thickness flaws on the order of 3% of the wall thickness or 5% of the wall thickness in this column. And so from that, we can perform these fatigue life calculations now that we've measured the fatigue crack growth relationships of these pipeline base metals. And so what that tells us is, based on these calculations in fracture mechanics, we can, the necessary minimum wall thickness to sustain pressure cycles that range from 3,000 to 1,500, and at a wall crack, or a crack in the wall that is 3% of the wall thickness, we need a thickness of pipe that is 0.62 inches. As we have a slightly higher flaw depth to begin with, that increases our necessary wall thickness up to 0.81 inches. And so to give us some frame of reference, we looked at what the current codes are for the natural gas. And so those are outlined in the ASME B31.8 code. And what that is based on, so if we assume we have a pipeline that is a X52, so 52 relates to the yield strength, and we assume that we're operating this under 3,000 psi pressure, this is not a fracture mechanics-based approach, but the thickness that you are required to have for this pipe would be almost a full inch thick. And so what this really means is that using experimental work and a fracture mechanics-based approach, we see that the hydrogen pipelines that the actual thicknesses that we need aren't any thicker than the current natural gas. Now, we wouldn't prescribe that the pipe should be thinner than the natural gas, but nonetheless, what it basically says is that we don't need a thickness premium on these hydrogen gas lines as opposed to natural gas, based on the current natural gas code. So I'm going to switch gears a little bit. I've talked about how hydrogen affects the mechanical behavior, but and in terms of how it accelerates the hydrogen or the fatigue crack growth rate. But now we're going to look a little bit how oxygen impurities can actually help mitigate the effect of embrittlement. So just a little bit, just to orient yourself, we basically looked at the potential energy of what, or actually, if we look at a surface of iron, so that's what these gold spheres really represent, are iron atoms, and as the hydrogen approaches, diatomic hydrogen approaches the surface, there's a certain activation energy necessary for that hydrogen to dissociate and then allow it to diffuse into the surface. So that's represented by EA on this curve, which is 0.1 electron volts. If we now look at that same surface, but use with the assumption now that there was already some pre-adsorbed oxygen on the surface, you can see that in order for this hydrogen to dissociate onto the surface, the activation energy is actually increased. And so using these density functional theories, it already tells us right off the bat that just having the presence of oxygen already pre-adsorbed on the surface makes it more difficult for that hydrogen to get in. So we wanted to take this type of analysis and really do some experimental work to try and verify it. And then this actually worked into and was built into a model with several of our collaborators. And so that's exactly what we did. We took an X52 pipeline. We did our typical tests. So we performed fatigue crack growth curves, or fatigue crack growth tests, in air, which are represented by the blue X's here. And we performed them in high purity hydrogen, and that is the red curve here. And you see hydrogen accelerated fatigue crack growth occurring at a low delta K and at a low DADN. And what we did was we took fixed amount of oxygen mixed species. So in other words, 10 ppm, 100 ppm, and 1,000 ppm oxygen. And those oxygen species were essentially introduced to the hydrogen gas, and we performed the tests in those environments. So first, looking at 10 ppm oxygen, what we see is we didn't see a significant change between that and the high purity hydrogen. So this told us that we didn't really have a lot of oxygen really already pre-absorbed onto the surface. But when we look at 100 ppm, what you'll see is that the curve actually follows the data in air up to a DADN approximately of 10 to the minus 5 millimeters per cycle. And then we begin to see hydrogen accelerated fatigue crack growth occurring, and it converges with the other curves. As we actually move to a higher oxygen content of 1,000 ppm, what we see is that that DADN on which the hydrogen accelerated fatigue crack growth occurs at is pushed to a higher value. And once again, we get accelerated fatigue crack growth rate, which converges with that in pure hydrogen at higher delta K. But really, we're seeing an incremental difference between different amounts of oxygen and when we see the onset of hydrogen accelerated fatigue crack growth. So all these tests that I've shown so far were tested in R ratio of 0.1. So that would be a more extreme loading ratio. So loads were essentially varied from 10% to 100%. So we also took the 1,000 ppm oxygen, and we tested it at a little bit more conservative R ratio of 0.5. And what we saw is that the data looks very similar to what it is in air. And so really what this is that very small amounts of oxygen impurities can help really mitigate the effect of hydrogen-accelerated fatigue crack growth. And it depends on a lot of variables, but some I've identified at the bottom through oxygen concentration, R ratio, fatigue crack growth rate, and the load cycle frequency. So just to go briefly into the model, I only have a few slides left, but just to kind of give you an idea how the model was fabricated or come up with. If you imagine here in the upper right corner, we have a crack represented by length A, and we have a mixed species of oxygen and hydrogen. And we have to assume that this crack is going to grow just by regular inert environment crack growth mechanisms. So it's basically a series of blunting and resharpening, as we typically assume in fatigue. So that crack's going to advance slowly just through this amount, introducing new fresh surface, and then it becomes basically a competition for the oxygen or the hydrogen to adsorb onto the surface. So if we look at the lower delta K region, or if you look at a lower stress, at a specific delta K, you get a specific amount of crack growth that will occur. As the crack advances, this fresh surface is exposed, and in this situation, there's sufficient amount of oxygen to fully passivate the surface, and therefore we don't see the effect of hydrogen-accelerated fatigue crack growth. Now, if we move to a higher hydrogen or a higher stress region, we're able to advance the crack even further. What this does is exposes even more crack surface area that is fresh and essentially untainted. And essentially, in this case, there is not sufficient amount of oxygen to fully passivate the surface. So this allows some hydrogen to get in, and this would be a scenario in which we begin to see hydrogen-accelerated fatigue crack growth because the oxygen is not able to fully passivate. So it really is just a competition between oxygen and hydrogen and for surface sites. So part of the model hinges on modeling, first of all, what the crack profile looks like, or the crack tip area. But the other part is the key assumption really is that it's rate limited by the amount of oxygen that can diffuse down the crack channel and absorb onto the surface. So in that, we used a steady state profile of oxygen, and we assume that the partial pressure of oxygen is consistent back in the bulk of the gas, but then it has a linear trend down to the crack tip. And then really it's just about modeling whether the oxygen delivered to the crack tip is able to be absorbed within a load cycle. So you can imagine the frequency that you're testing this at affects how much oxygen is able to travel down there, how fast it's able to travel down there. And also the R ratio kind of dictates what the crack profile will look like. In other words, is there a pulsing effect of gas species? So without getting too far into the details, really it's just a matter of the flux of this competition, really, of oxygen getting to the crack site and it being able to absorb. And so the model really is reflected in this equation in the bottom right corner. And what it's really telling us is that hydrogen uptake and accelerated fatigue crack growth will occur when oxygen coverage is not sufficient to fully passivate the surface. So we applied this to this X52, and I'm not going to really show how the correlation occurred, but it actually showed some pretty good correlation, in other words. So all these variables can really be modeled and really help the possibility of mitigating the effects of hydrogen embrittlement. So in summary, I'd like to basically just briefly outline what we found. We basically saw that the strength of pipelines does not necessarily dictate how they behave in hydrogen. There's typically this thought that the higher the strength, the more susceptible they are. It's actually more geared towards microstructure. That seems to be more of a dominating effect. We looked at two different welds, a friction stir weld as well as a gas metal arc weld, and they actually showed fairly similar resistance, which potentially has some benefits in terms of cost savings from the friction stir weld standpoint. Overall, the welds had a slightly higher fatigue crack growth rate than the base metal. And then doing some calculations, actually putting pen to paper and saying, okay, now that we have some experimental data, can we actually calculate what pipeline thicknesses are required to sustain a life of, say, 50 years? We found that given the current natural gas codes, those appear to be conservative enough for what we are looking at. And then finally, just from the kind of tangential study on oxygen effects, we found that low levels of gas species, such as oxygen, really help enhance or could potentially enhance safety margins by this mitigating effect that they have on hydrogen embrittlement. So the remaining challenges that we're looking at, we're actually looking at doing some higher strength pipeline steels, such as X80 or X100, and seeing if we can somehow see if those will qualify. Do they show similar trends to these X52 steels? And can we look more deeply at the microstructure? Because there's going to be a lot of different microstructural grades put in the ground. And we don't want to have to be able to do testing on every single pipe that goes in the ground. So really, we're working towards ultimately this model that will allow us to look at the microstructure and determine if that microstructure is sufficient for hydrogen use. And then we can develop these predictive models that are based on the physics of hydrogen diffusion and what's actually going on in the material, such that we could select steels that are optimal for hydrogen without having to do experimental tests on every single one of them. So with that, I will conclude my discussion. And as Chris mentioned, these are where the questions are, if you would have any for me. And I'll pass it back to Neha. So thank you.
Thank you, Joe. So we have a handful of questions. So the first one was whether or not friction stir welding happens in the field.
So that's a good question. So friction stir welding is a process that is can be challenging in the field because it does require some big equipment. It requires less manpower, I'd say, but in general, it does require some specialized equipment, which does have a cost premium, but it can be done in the field. But as of now, like I said, it's kind of a balance between man hours for the typical MIG welding or more of an upfront cost of the equipment for friction stir welding to allow it to be done in the field.
A couple of questions about impurities. So I think maybe you sort of answered some of them towards the end, but one of them was why the choice was made to use high purity hydrogen gas rather than a lower quality to better simulate what's put in the field. And then another one was whether it's likely that impurities of other gases other than oxygen would similarly slow down crack growth.
Yeah, so those are two very good questions. So the real reason we started looking at pure hydrogen is we really wanted to see the worst case scenario. We wanted to be as conservative as possible and look at what the extreme environment would be, which would be pure hydrogen without any impurities. So that's why we started looking at that. The second question, which was related to, is there other impurities? Carbon monoxide has a similar effect to oxygen. So there are other gas species that can have similar effects to oxygen. And this is an area that there has been some research on, but it's interesting to see that it is basically different gas species can behave similar to oxygen in mitigating it.
There's another question about whether you studied the effectiveness of applying sealants to the welds that protect the welds so that crack growth isn't a problem in the weld region.
Okay, yeah, so so we specifically didn't look at any type of seal or coating applied to the inner diameter of the pipe. That is a possibility. One of the issues with that would be knowing how that seal stays in place throughout the life of the pipe, and then also the cost is obviously going to be driven up by having that seal or coating on the ID of the pipe. And so these are possibilities, but in general, we didn't look. We just looked at base material, bare material, which would again be the worst case scenario.
Another question is whether the crack growth is exacerbated by the fluctuations in pressure or like the absolute values of pressure.
Yeah, so it's actually that's a good question that I probably didn't address that well at the very beginning. So the current pipelines that are in use, as I mentioned, are basically operated at constant pressures. Now they aren't operated at that high of pressures. They're probably operated in the order of 12 to 1400, 1500 psi. And we're thinking ahead, thinking, okay, we're probably going to be operating these pressures at closer to 3,000 psi when the pipeline economy is much more mature. But really, it is the fluctuations that brings about this other phenomenon. So at a constant pressure, you really have to worry about the fracture toughness of the material. But in cyclic pressures, if the pressure is fluctuating, that's when you introduce this phenomenon of fatigue. And that is what seems to be really helps drive the crack much further than, or it seems to be, it's essentially a different phenomenon. So it really is the fluctuations that's driving the crack in this case.
Did you ever study steel pipe with a cured in-place pipe liner installed?
Can you repeat that? Was it a cured in-place sealant? Is that what I heard?
Yeah.
So no, that goes back to one of the previous questions. We haven't looked at any type of sealant on the surface of the weld as a means for kind of removing the weld from really being exposed to the hydrogen. We have not looked at that.
I have a question on whether you've done cost comparisons between steel pipes and carbon fiber pipes. So maybe I can speak to this because we did a little bit of this at DOE.
Yeah, if you wouldn't mind.
I have estimated the current cost of fiber reinforced pipelines, and the actual values you can find in our multi-year research development and demonstration plan online. But generally speaking, because it's so much less expensive to install, the costs of FRP tend to be lower than those of steel. But it's important to keep in mind that FRP is manufactured at lower diameters than steel transmission pipelines. So FRP is usually manufactured at 4 inches or lower. So in higher transmission applications, so like oil and natural gas lines can be much bigger than that. And so in a mature market with higher diameters, it may not be a viable alternative. On how water in the gas or liquid phase would impact your results.
How water would?
Yeah.
Okay. Yeah, in terms of, it's really about trying to understand what's going on with the oxygen seems to be the pertinent component in that, and that it's present in oxygen, obviously, it's present in water, and it's present in carbon monoxide. So really, oxygen can have kind of an effect that would really, I think to answer that question, you need to know what's going on with the water itself. Is it able to dissociate into oxygen and hydrogen and then can cause some sort of mitigating effects? We haven't specifically looked at water just because we often measure water vapor in our test gas just to ensure that it is lower, and we're testing in as pure hydrogen as possible. But we don't really look at adding incremental amounts of water vapor as we did for this oxygen content. But it potentially could have an effect just because there is the presence of oxygen species in that water vapor.
All the questions that have come in so far, we can hang on a couple minutes to see if any more come in. But
okay.
it doesn't look like we have any more questions. So thank you very much.
Yeah, thank you. I appreciate all who listened in, and appreciate your comments and your questions. So thank you very much.
Great. So as Chris mentioned, this webinar is being recorded, so it'll be available online later. And with that, we can end the webinar.
Yeah, and if I may, thank you both very much, Neha and Joe, for the interesting presentation today. I think everybody learned a lot and was pretty engaged, so really appreciate it. That's going to conclude the webinar today. Joe, if you would go to the last slide there, I think we have one more with some contact information there. There we go. If we didn't get to your questions today, or if you guys think of any attendees think of any additional questions, please feel free to email the presenters directly, and they will try and respond in a timely manner. I'd like to thank everyone for joining in and remind you that the webinar and slides will be available online at the Fuel Cell Webinars website, shown there as the first link, in about 10 days. Also, I encourage everyone to sign up for our monthly newsletter, which includes upcoming webinars. You can sign up for that at the second website shown below. Have a great week, everyone. Goodbye.